The answer, he declared, was 5,050, 50 times 101. There were 50 pairs of whole numbers, with each pair adding up to 101, 1 plus 100, 2 plus 99, and so on. Gauss's father, Gerhard, worked variously as a gardener, bricklayer, and canal tender, and assumed his son would also earn his living as a labourer. However, Gauss's mother, Dorothea, and his uncle Friedrich encouraged and fostered the child's interest in mathematics, and in 1792 the Duke of Brunswick granted the 15-year-old a stipend to attend the local Collegium Carolinum, today the Technische Universität Carola Wilhelmina zu Braunschweig, Technical University of Braunschweig. The young man was soon deep into the study of number theory. He derived the binomial theorem, a central result of number theory, and independently discovered what is now known as Bode's law, a numerical relationship that relates the sizes of the orbits of successive planets. In 1795, Gauss moved from Brunswick to the University of Göttingen, where his career and reputation flourished. In 1807, at the age of 29, he was appointed director of the Astronomical Observatory, and for the next 10 years he worked mainly on mathematical problems in astronomy, using the now popular methods of calculus. He also perfected and published his least squares method for finding the best mathematical fit for a set of observational data marred by random errors or noise. The method proved itself in verifying the orbit of the asteroid Ceres, until then something of an enigma because of the difficulty of making accurate measurements of its position. Before long, Gauss's interests had shifted to geodesy, the study of Earth's shape and dimensions, and potential theory, an emerging mathematical method that was found to be particularly useful for analysing Earth's gravitational field. These would set the scene for his future work in geomagnetism. Gauss was encouraged by von Humboldt. The two men first met in 1828, and it is likely that they discussed the problems involved in obtaining absolute measurements of magnetic intensity and mathematical representations of Earth's magnetic field. Also on the agenda would have been von Humboldt's vision of a worldwide network of geomagnetic observatories. Within the next few years, Gauss had solved the absolute intensity problem, produced a mathematical model of Earth's magnetic field, built his own geomagnetic observatory, and thrown his weight into the geomagnetic observatory movement by setting up Göttingen Magnetischer Verein, Göttingen Magnetic Union. Gauss's answer to the intensity problem was as simple as it was ingenious. The obstacle to calibrating the period of oscillation of a dip needle or compass had been the need to know what amounted to the strength of the magnet used for the needle, in technical terms, its dipole moment. The period of oscillation depended on the product of this dipole moment and the Earth's magnetic intensity, that is, the one multiplied by the other. Gauss figured that by making a second measurement he could obtain the ratio of the two, the one divided by the other. He took another compass, and while letting Earth's magnetism pull its tip towards the north, he arranged the original magnet to pull it at right angles, towards the east or west, like a rotational tug-of-war. The angle at which the compass needle ended up depended on how strong the magnet was compared with the Earth's magnetic intensity. Once both the product and the ratio of two things are known, it is a straightforward matter of arithmetic to untangle them. Gauss was able to calculate not just the intensity of Earth's magnetism, but also the dipole moment of the magnet. For obvious reasons, this became known as the oscillation deflection method.